history of time and told us that as you view information from this perspective, looking back, you have a very different perspective of that time than looking forward. The universe started off hot and dense, and it expands, and it expands, and it expands. Not by there being new space. There's no new space. Outside the edge of the universe, if there is an edge or whatever that means, there's not other space to expand into. The universe gets bigger by space stretching. It's as if you took a balloon and blew it up halfway. Get a nice big balloon, up this big, look this big, okay? Now you glue on it some pennies. Each penny represents a galaxy. Oh, galaxy, hundreds of billions of stars. And you blow up some more. What happens to the pennies, one relative to the other, as the balloon gets bigger? They move apart. Are you getting more rubber? No, the rubber's just stretching. And that's how the universe gets bigger also. No new space. Just the same space is stretching. That's why the universe gets cooler as it gets bigger. And as space stretches, that has a phenomenal effect on the perception of time. We look back in time. The Bible looks forward in time and tells us 6 days passed. We look back in time and say, there were dinosaurs 150 million years ago. There were insects 550 million years ago. There were solid rocks 3.5 billion years ago. And the Bible says that all happened in day 3, 4, 5, and 6. And they're both correct according to Albert Einstein. Think of what happens here now. You've got the beginning of, the Bible sees time from here. Let's go back and pretend there's a consciousness back there. God or what, anything back at the beginning of time. And this consciousness happens to own a laser. Obviously, there were no lasers back then. There were no people. There was not, just energy, and a few particles of matter. But this consciousness, this make-believe consciousness that we're going to try to understand, owns a laser. It sends out flashes of light, like a flash on your camera. It sends out a single flash of light. And another second later, it sends out another flash of light. Now, on the flash of light is imprinted some information, because you can do that on light, fiber optics. I'm sending you a flash of light every second. Every flash of light has written on it, I'm sending you a flash of light every second. First light goes out, second light. Light travels at 186,000 miles a second. So between the first pulse and the second pulse, there's a whole second of time. There's 186,000 miles. That's a lot of time and a lot of space. 186,000 miles. And now these pulses are going to travel through space and time till they're going to reach us here in Jerusalem on the 18th of September, Friday, about 4 minutes before 5 o'clock in the evening. And we've got this big dish antenna. Wango! The first pulse arrives. Wow! And we decipher it. A pulse every second. A voice from outer space. Break out the beer. Bring in the newspapers. Wow! My golly! But look what happens to the pulse. The first pulse comes out. The second pulse comes out. But now they're going to travel through time and space. What's going to happen to the pulses? What's space doing in that time? So what's happening to the pulses? They get further and further and further apart. The first pulse arrives. Bingo! A second later, does the next pulse arrive? No. Wait a minute. Who said no? Said no? There's God back here speaking. Calling God a liar? God said, every second I'm sending you a pulse. I get out here. Bingo! The second pulse does arrive a second later. Because when you send information across space, the transfer of the information changes it, and the author of the Bible wanted to make sure that in the 1990s, when we discover that we wouldn't be saying there's something wrong with the text. There's nothing wrong with the text. It was 6 days. It contained all the ages of the universe. But when we perceive that time from our perspective, it's billions of years. That stretching of space is called a redshift. I want to quote from you now from an extraordinarily good book, mine, but which quotes from an even more extraordinary book on cosmology, probably the leading book on cosmology, on the science of the universe, Principles of Physical Cosmology by Peebles, P.J.E. Peebles at Princeton University Institute of Advanced Studies. This is probably the leading textbook in graduate school cosmology, Principles of Physical Cosmology. Okay, and I quote it directly. In my book, I not only put it in italics, but it's probably the most important sentence in this concept. It's in italics and underlined on page 54. Now, the stretching of information as you go through space is called the redshift. Why is it called the redshift? Because red light has a long wavelength. Blue light has a short wavelength. I don't have a red pen here, but it would be that red. If blue light were like this, then red light would be like that, okay? In fact, supposing Zola were having like a big party, he says, by golly, in Israel, one of the colors is blue. I want to bathe this party in blue light, okay? So Zola, having a direct line to, we know who, phones back and says, God, send me some blue light. I mean, God can paint the whole universe blue light, right? So God from here sends out the blue light. But as the blue light travels through space to reach us here in 1998, it stretches out and arrives as red light. Zola, what are you doing? I ordered blue light. But that's the way it is when you send information through space. It stretches out. And this quote, so the jargon is called a redshift. The stretching of information is called a redshift. The standard interpretation, I'm quoting directly from the physics textbook. The standard interpretation of the redshift, the stretching of information, as an effect of the expansion of the universe, predicts that the same redshift factor applies to the observed rates of events. We see a rate that took 15 billion years. The Bible sees 6 days. And they both may have happened at the same time. What's nice about giving this lecture in the 1990s is we now know how much stretching of space there's been since matter formed from the energy of the Big Bang. And that stretching of space is a known number. Now put this back just for a moment. The general number, the approximate number, from this moment here to out here, because there hasn't been a vast change in this region, from here to here, is a 1 with 12 zeros after it. It's a million, or a million squared. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A million. The universe is now a million times bigger than it was here. Okay? Which means that if you sent out information that was being a second apart, by the time we would get it here, ages later, any guesses for how many seconds apart it would be? A million seconds. Conversely, if we had a million seconds worth of events, like just a series of things that a person with great binoculars could see it from, of course you couldn't see this distance, but in theory, if you sent this million seconds worth of information back in time, what would it look like? Look like a second. All the events, it's like Hadassah looking down on the earth. It'd be super fast, like a video, and super fast forward. A million seconds would pass in 1 second. All the events would be there. Of course, our eyes wouldn't be able to discern each one because it'd be a blur. But if you had a phenomenally fast camera, you could record it, then you could play it back on slow motion if you had a million seconds to spare to get exactly what is right. These are datas. They have nothing to do with Zola, they have nothing to do with Schroeder, they have nothing to do with Jerusalem or Bible study. These are numbers that come from every leading physics textbook. I'll tell you, a while ago, in the spring of this year, I was at Northwestern University. The physics group came to the lecture, and I said, I'm not going to quote from another physics textbook that's well known, and it's called The Big Bang. And one of the physics students, I've never met him, I don't know his name to this day, yelled out from the audience, oh, you mean the book The Big Bang, written by the astronomer from the University of Chicago, Joseph Silk? I said, yes. Now, any speaker, that's exactly what he wants. That a person in the audience, totally unknown to him, confirms the origin of the information. The million number is a valid number. We say the universe is somewhere between 14 and 17 billion years old. So I'm just taking a number in the middle, because then we'll get to some more exact numbers. I think the 15 billion years. $15 years divided by 1,000, or 0.15 years. Not even a year. The entire controversy comes down to a number not even a year. I mean, there's almost no, what's the difference? It's not billions of years anymore. It's not even a year. But fractions are messy, and who wants to be stuck with a bunch of fractions? So I thought I'd change it into days by multiplying by 365, right? Anyone want to make a guess what that comes out to be? Well, almost. Comes out to be 5.5 or 5 3/4. I have nothing to do with the numbers. I'll tell you, when I did this calculation, it took a long time to discover enough about the universe to understand it. I ran to my wife, Barbara, who is the author of a very good book called The 13th Hour. I recommend it, published by Signet. If you want to know the inside understanding of what's going on in the Middle East, that book is extraordinary. Any event, I went to my wife, Barbara, the author of The 13th Hour, and said to her, I was covered with goosebumps. I said, I can't believe these numbers. It matches exactly. But that's a generalized number. There is, in fact, the option of doing it exactly, because we now know the exact difference between the energy changing into matter, where the clock begins, the 6 days. We now know the exact relationship between these two. And I'm not going to get into the math. I have it in detail in a chapter, but I tell people just skip over those about 4 pages if you're frightened by the math. It has to do with trying to understand how the flow of time would exist, and it's an integral formula. Unless there are persons who have advanced math degrees here, or let's say if take math at university level, I'll skip it over. If most of you, how many have not taken mathematics at university level? No, have not taken. Okay, so most, I don't want to bore you with it, but it's not complicated. It's first year, but it has to do with an integration. But just to get the general picture of how the time would flow, okay? Supposing the universe was this big, okay? And it doubled in size. Let's say it took an hour to double in size. Remember what Peoples wrote. Every time the universe, with this redshift factor, every time the universe doubles in size, the perception of time halves. So supposing the universe were this big and it took an hour to become this big, doubled in size. Now it's twice as big. So to double in size now, how much time will it take? No, it's twice as big. 2 hours. And to double in size again? And then? Yeah, 2, 4, 8, 16. That's called exponential development, or an exponential flow of time. And that exponential relationship is in fact the relationship of the flow of time, because every time the universe doubles in size, the perception of time varies by a factor of 2. This is 1/3 of what was once a whole ammonite from 170 million years ago in Charmouth, England. I don't know if you probably can't see it too clearly from where you're sitting, but you'll notice that the circle, there are swirls on this. It's the cousin of a modern snail. Each swirl is a given factor bigger than the previous swirl. It's the exponential relationship, just like the doubling of the universe, 2, 4, 8, 16. It's the exact same relationship. And that exponential relationship shows up literally throughout the universe. It shows up in ammonites. I had these the other day with Zola, but when I see him picking up my fossils here, I have to be careful and guard them. This is a nautilus seashell. It's quite beautiful in the original. Come to my home one day, you can see it. From Cape Town. This is a whole one of these. It's an ammonite, again, from Regis in the southern coast of England, 270 million years old. The same spiral. I don't know how well you can see it in the back. These are the seeds of a sunflower. My daughter took the picture. Her daughter took the picture. If you look carefully at a sunflower, the seeds are the same exponential spiral. And this probably is too small to see, but it's a galaxy. The stars of a galaxy. From galaxies to sunflowers. The exponential relationship. It is something to shake your head about. It's amazing, isn't it? It's just scary. It's everywhere in the universe, and it's what God chose for the days as well.